Here, I just list a few. The first is the vertical velocity, which is the upwelling, downwelling patterns, and the other is mixing. Okay, actually, the ocean mixing part is very interesting because by doing this, we realize that for the vertical transport, not only the dipycnal mixing, which is the mixing across the isopycnals, but the mixing along isopycnal also contribute to the vertical transport, particularly for region you have very steep isopycnals. For that region, the isopycnal mixing actually contribute a lot to the vertical exchange of temperature, salinity, and material. And also the mesoscale eddies have some contribution to this, mainly kind of act as the something called Bowler's velocity in the estimate. I have already did some result about this, get one paper published last year. So for this, I will show some result from this. The ocean mixing is something I'm working on. For this, maybe in the future. This is the result from the on the estimates of the temporal mean vertical velocity from for the global ocean at 3 different depths. Okay, this is the vertical velocity at 200 meters. So it shows a very conventional pattern. People in oceanography all know that, like Ackermann pumping in the subtropical ocean basin, you have very strong upwelling along equator. Those are very known patterns. But if you go deeper, I mean, go to 1,000 meter or 3,000 meter, you find that the strongest upwelling, downwelling mainly occur again in the Southern Ocean and North Atlantic Ocean. So those are the regions you have the strongest upwelling, downwelling. The reason is actually quite simple. Is for this region we know we have the strongest current on the Earth. That's the ACC. Okay, you have ACC move around, strongest current move all the time, and you have a lot of bathymetry. Okay, you have a lot of mid-ocean ridges, some very big topographic features. And when the ACC flow over this bathymetry, you generate upwelling, downwelling if you look at certain depths. Okay, those are very important. I mean, those are not particularly important for people who care about, who think the ocean is in a steady state. If it's in a steady state, those features, I mean, you can imagine if you have a bathymetry, you have current move up, move down, you transport some heat up, then you move the heat down. So if it's a steady state, it seems doesn't matter that much. However, we know that we are experiencing a non-steady state. We are experiencing warming from the surface. Or you add more CO2 to the ocean. You have some CFCs added to the ocean. What we are dealing is a non-steady state. So in that case, these structures will act more like an elevator. Okay, they can kind of transport. You get up, you get some material or signals. Then when you move down, you just push that to the deep ocean. It plays some very important role for the vertical transport of property material in a non-steady state. Okay, that's I think this kind of this pipe-like structure at high latitude is very important for transporting those abnormal climate signal or material to the deep ocean or to the upper. It's very important for the vertical exchange in non-steady states. And the one problem is, one kind of very, I think, quite important implication for this structure is when people look at the upper ocean, deep ocean exchange, sometimes they use the Zuno average picture. Like I guess many of you are quite familiar with those 2-cell pattern, meridional circulation, you have the 2-cell pattern. But the problem is when you do the Zuno average, those features will gone. I mean, those features related to bathymetry. When you do the Zuno average, those bathymetry-related features are gone. What you can see is just the wind-driven pattern, the wind upwelling. So that's why a lot of paleo works, they attribute the vertical exchange, the long-term change of the vertical exchange to the change in the wind. Okay. The one reason is this pattern is gone in that Zuno